Good morning to our lecturers and fellow engineers. Welcome to today's Sustainability Forum. We are currently living in the era of artificial intelligence. From ChatGPT to advanced medical research, AI is changing the world. But this digital revolution has a massive physical footprint. Right now, here in Malaysia and across the globe, massive AI data centers are being constructed. These facilities house tens of thousands of powerful processors, and they consume an astonishing amount of electricity. A significant portion of this power isn't even used for computing. It is used to cool down the servers so that they don't catch on fire. To solve this sustainability crisis, the tech industry is turning to the principle of electromagnetic field and waves. Today, our panel will discuss a revolutionary technology called silicon photonics. Joining me today are four leading experts: our lead network engineer, Mr. Ethan, an energy analyst, Mr. Kao, an environmental auditor, Mr. Benjamin, and a technology policymaker, Mr. Ngai Ho Yin. Let's start with the root of the problem. Currently, data centers use traditional copper wiring to connect servers. Why is this outdated? And how exactly does silicon photonics use electromagnetic waves to solve this problem, Mr. Ethan?
Thank you, Mr. Richard. The core issue with copper wiring is electrical resistance. In a traditional data center, data is transmitted as electrical currents moving through heavy copper cables. When you push massive amounts of data at high speed, the electrons experience resistance, which generates extreme levels of heat and is incredibly inefficient. Silicon photonics completely changes the medium of transmission. Instead of using electrical currents, we use infrared lights, which is a form of propagating electromagnetic waves. We place microscopic lasers directly onto silicon chips. Then, these lasers generate infrared EM waves that travel through hair-thin fiber optic cables. Because photons, which are the fundamental particles of EM waves, do not have any mass or electrical charge, they do not suffer from the same resistance as electrons. They travel perfectly down the glass core using a physics concept called total internal reflection.
Okay, I'm sorry, but I must interrupt, Mr. Ethan. So we are replacing electricity with light, but how does that allow us to send more data?
Well, that's the beauty of wave physics. We use a technique called wavelength division multiplexing, or WDM. Because we are dealing with EM waves, we can send multiple different frequencies of infrared lights down the exact same fiber optic cables at the same time. They do not interfere with each other, so this means that a single tiny fiber optic cables using EM waves can carry more data than a bundle of thick, heavy copper cables. And it does so at the speed of light with virtually zero heat generation.
I see. So that is fascinating engineering. So we are swapping heat generating electrons for highly efficient infrared EM waves. Let's talk about the impact of this application. From an energy and sustainability perspective, how much of a difference does this really make to our environment, Mr. Kao Koshet?
The positive impact is absolutely game-changing for our environment. As mentioned earlier, the heat generated by traditional copper wires forces data centers to run massive industrial air conditioning units 24/7. In a traditional data center, nearly 40% of the total electricity consumed goes purely to cooling systems. By transitioning to silicon photonics and infrared EM waves, the heat generation drops drastically. This slashes the power consumption of the facility, which directly reduces the carbon footprint, especially in countries that still rely on coal or natural gas for electricity. But there's a second equally important benefit: water conservation. Traditional data centers use massive cooling towers that evaporate millions of gallons of fresh drinking water every month to keep the copper system cool. By using heat-free EM wave transmission, optical data centers require significantly less water cooling. This preserves our vital freshwater reservoirs for society and agriculture, ensuring a much more sustainable ecosystem.
It sounds like a perfect solution for having both electricity and water. But as engineers, we know that no technology is flawless. We must evaluate the complete life cycle. As an environmental auditor, what are the hidden dangers of this technology? Are there negative impacts on health or the environment that we are ignoring, Mr. Benjamin?
Yes, unfortunately, there are severe environmental costs that occur long before the data center is even turned on. To generate and detect these specific infrared EM waves, we need highly advanced laser and photo detectors. Manufacturing these optical chips requires mining toxic rare earth elements like indium, gallium, and germanium. The mining and refinement of this specific metal cause devastating ecological damage. It leads to severe soil degradation, toxic chemical runoff into local rivers, and hazardous health conditions for the mining communities. Furthermore, we are facing a massive e-waste crisis. Silicon photonics integrates microscopic optical components directly alongside electrical components on a single microchip. When these servers eventually break down or become obsolete, they are nearly impossible to recycle using current methods. You cannot easily separate the rare earth optical metals from the silicon. Because of this, thousands of tons of toxic optical hardware are destined to end up in the landfills, slowly leaching dangerous chemicals into the groundwater.
That is a sobering reality. We are trading high carbon emissions for toxic rare earth mining and complex electronic waste. We cannot simply abandon AI, but we cannot destroy the earth to power it as well. As a policymaker, how do we solve this? What engineering and societal solutions do you propose to mitigate these negative impacts, Mr. Ngai?
To ensure this technology is truly sustainable, we must implement a strict two-pronged approach involving both government policy and engineering design. First, we must mandate a circular economy of optical hardware. Governments must enforce extended producer responsibility (EPR) laws. This means tech companies are legally responsible for the entire life cycle of their optical chips. Engineers must adopt design for disassembly principles, manufacturing photonics chips so that the rare earth elements like indium can be chemically extracted and reused, drastically reduce the need of destructive virgin mining. Secondly, regarding the society impact, we must enforce strict energy zoning laws. If a tech company wants to build a new high-speed optical data center, they must completely decouple from the national power grid. We propose a policy where data centers are required to build for fund localized renewable energy sources such as solar farms or hydroelectric plants to power their operations. They must generate the energy they consume, ensuring they do not steal resources from the local society.
Okay, thank you so much, Mr. Ngai. And thank you as well to our dear panelists here. To summarize our discussion, the application of infrared electromagnetic waves through silicon photonics is an absolute necessity. By replacing copper wires with light, we can drastically reduce the massive electricity and water consumption of modern AI data centers. However, as responsible engineers, we must acknowledge the limitations and hazards of our tools. The environmental cost of mining rare earth elements and the impending e-waste crisis cannot be ignored. By combining innovative recycling engineering with strict renewable energy policies, we can harness the power of EM waves to build a truly sustainable digital future. Thank you so much to our dear expert panelists, and thank you all for watching.